Hi guys, this will be an introductory video for the heat capacity lab. Heat capacity is given to you in this formula that heat, and don't know which heat yet, leaving or entering the thing, is given by some constant that's determined by the thing itself. So copper will have one, water will have a different one, ice will have a different one still, times the mass of the amount of material you're heating up and the change in temperature. So there's a little bit of an ambiguity that shows up here and here, and it's kind of deliberately ambiguous because you might care about the heat lost or the heat gained by the thing. So specifically, if I go from some initial to some final temperature, and imagine that this thing is heating up, like it's getting hotter, this will be larger than this, therefore heat will be positive. This will be, in that circumstance, heat gained. If you flip them, it will be the amount of heat gained not by the sample, but the amount of heat that's lost by the thing that's heating it up. I'll give a specific example because that sounds a little bit like vague. So this would be heat gained by sample. Okay, so what you guys are going to do is essentially a calorimetry experiment with a calorimeter. But made by you guys. And calorimetry is really energy conservation, but it's energy conservation with this spooky invisible form of energy called heat. So here's an example of calorimetry experiment where I have a hot chunk of metal and I dump it into some cold water, and I want to make sure that it's really well insulated so no heat escapes through this. It's got a lid to prevent evaporative cooling, like when you blow on coffee to cool it down, and it's got a nice thick insulating edge. And then if I wait for a while, what's going to happen is they're going to go to thermal equilibrium where they have this shared final temperature. Okay, so really what's happening is we're conserving energy. The heat lost by the metal will be gained by the water. So aside from the clunky subscripts and superscripts, what a beautiful equation, Q equals Q. The problem is that you got to make sure that these are set up correctly. So what is the heat gained by the water? So that would be C water, I'll use W, mass of the water. And then for the metal, this will be C metal, mass of the metal. And then T's. So this is where you can run afoul of sign error. So this thing is going to lose energy, right? It's going to lose energy, so the amount that's lost is positive. I'm going to say that again because you got to kind of think through a double negative sign. The amount that this thing loses is positive. It loses a positive number of joules, right, as it cools down. So I got to make sure that this is positive, and in that case, its initial temperature, so T hot in my diagram, is going to be greater than TF. Positive number. The amount that's gained by this is also a positive number. The other way to think about this more succinctly is there's no way these things are going to be equal if one's positive, one's negative, so that's what dictates the signs. So final temperature is greater than T cold, the initial temperature of the water. This is our equation. So what you guys will be doing is this, and we'll show off the experiment itself. 4 data points is probably going to be about as much as you can get, but you're free to have more. And you're going to use it to find this. And what we'd like to do is plot this in such a way that we have the simplest measurement from the graph of the heat capacity of the metal. So probably the easiest thing to do is, the most direct way what you're doing is you're using this as your independent variable. So the mass of the metal, you'll have, hopefully at least 4 chunks, mm, and then you're observing or calculating the amount of heat gained by the water. So the direct measurement itself is going to be this TF. That's what you measure with the thermometer. But just to make our lives simple, because we just want to look at that, let's just plot this whole thing as y. So this is y, so Q gained by the water, all on the y-axis, and then really let's make our lives simple, super simple, and call all of this x. So if this, the initial temperature, which will be the temperature of boiling water, minus TF, this whole thing is on the y-axis, this whole thing is on the x-axis. You'll get some pretty scruffy looking data is my guess. So the slope of this will be C metal. But of course you have, as you always do, error bars. So that discussion is in the lab manual itself. And so doing this kind of gives twice. One, it lets you find CM pretty easily, and two is that when you calibrate your calorimeter, what you're basically doing is you're finding the size of the error bar, how much this grows for every minute your calorimeter is sitting there coming to equilibrium. So that's the calibrating the calorimeter part, basically figuring out what delta Q over delta T is, where that's time. So how big those error bars grow every minute. So this is how you would do this in a labby lab. Of course, safety first. Can I get those glasses from you?
Here you go.
Seriously though, don't burn yourself when you're doing this. So this is an actual calorimeter. You notice the wooden top is good enough. Really what you're trying to do is prevent the coffee blowing to cool down effect. There's a bit of a stir. Stir might be a grandiose word. Basically, you splash it around a little bit to help the water convect. And then inside, this is an old one. Basically, it's got some really carefully insulating material. So this metal is not allowed to touch this metal. Honestly, since this was made in, like, I don't know, 1980, the technology to make vacuum thermoses has advanced a lot. If you don't have a good vacuum thermos, 2 nested styrofoam cups will work. And again, this is really to hold the instruments. So this is a nice calorimeter. And this is a thermometer. So mine's wonderful because it measures Celsius and it's graded. I think each one of those ticks is 0.2. So right now in this room, it's 21.8 degrees Celsius. That will be precise enough. And that goes through this, probably a little bit off the deck. And the way that I would do this in lab, which is basically what you're going to do just with like kind of more homemade equipment, is I would have some metal samples. So here's a bit of steel, here's some aluminum, here's wrought iron, and here's some brass. And what I would do is I would take these and I would put them in boiling water. So that would be my tea hot, basically get this up to a boil. I would put a known amount of water in this. So you can use the conversion in between water's volume and temperature. So 100 milliliters of water will probably be good enough. Glug, glug, glug. Put 100 milliliters of water in there. And then after, be patient, I would have the sample come up to a final temperature here, pick it up, and then dunk it in the water in there, and then again be patient, maybe give it a little bit of a stir, wait until this shows that I've come to equilibrium. So it turns out you can do a pretty damn good job of this at home. What you have to do is find a metal sample. If you find a different one, that's great. Here's my metal sample. These are post-1983 pennies that are 97.5% zinc. If they're really, really schmutzy, what you can do is clean them up with a little bit of vinegar and salt. Thanks to Chris for pointing that out. Works amazingly well. And acetone as well also works. I guess we drank all the acetone. But you want pennies that look like about this
the quality of our videos.
Yeah, you gotta get worked up for the videos. Okay, so now calorimeter. Nested cups work, styrofoam cups. Glass does not work. So glass actually will conduct heat at about 10 times the rate of a calorimeter like this or a vacuum thermos. Ceramic also does not work. These are bad, can't use them. Thermoses may or may not work, so hide the logo so you don't know why it's cheap. But here's a pretty inexpensive thermos. Goes clunk. It's actually not vacuum sealed. You can also see the lip around it. This actually is a nice vacuum sealed thermos. And the one that currently contains my coffee is also a nice vacuum sealed thermos. And ultimately know that whatever you're using is good enough in the calibration stage, so we'll post a number for the amount of heat that you lose that's good enough. And if you can beat that, then less heat than that escapes your calorimeter per minute. That's fine. Okay, so what you will probably realize if you think about it for 10 seconds is that an individual penny is going to be tough. The good thing about it is it heats up pretty fast. The bad thing about it is that it's kind of difficult to manipulate in my boiling water. Secondly, I want to get all that water off, and by then it may have cooled down. So what you can do is make slugs. So here I have a nice slug with a cool carrying handle of 10 pennies in a bundle, and then really quickly kind of daub it off. It's going to cool down less. Into the calorimeter it goes, and I have a homemade lid. Again, the lid is really just to prevent evaporation. You can have a stir or two, or you can do that carefully. So now I can watch this. I don't know if you can see this closely, but it was 21.8 degrees in the classroom, and now as the metal cools down, it's going to eke up to probably like 23 or something maybe.
Turn it a little bit further this way. Keep twisting it. There you go. Now I can see the numbers.
Okay. So I don't know how long we actually left that in. So the one thing to note if you do the penny bindle thing is that that was 25 grams, so 10 pennies. And the wire itself, this much wire is about a gram. So you got to figure out the mass of the wire that you're using, or at the very least come up with an approximate number and put an error bar on your value of mass when you do that. So this turns out to work just about as well as that if you do it right. If you have an infrared thermometer, you can do that. You would just take the measurement really quickly by removing the cap, and then you'll have 4 different mass measurements. Error bars come from calibration, these come from math and your assignment, your personal assignment of delta M and delta T based on whatever thermometer you use, and then that'll find C. So again, don't burn yourself while doing this, or if you do, don't let us know about it. Okay. Let's give this one more stir. It's made it up to a lordly 22 degrees. So you'll do a more conscientious job than this, and you'll have 4 data points to take. Right? Good luck.